Hello, my name is Saru Yamamoto from Keio University. I'll talk about pinch force measurement using a geomagnetic sensor. As background, we focus on the importance of hand muscle strength in medical practice. Hand muscle include grip strength, which is the strength to hold an object, and pinch strength, which is the strength to pinch an object with fingers. And pinch is further subdivided into chip pinch, which is pinching with the fingertips, and key pinch, which is pinching object with the side of the fingers. However, there are few opportunities to measure hand muscle strength, and commercial measuring equipment is expensive and bulky, so making it difficult to spread measuring equipment to ordinary households. In this study, we aim to develop a pinch force measurement device utilizing a smartphone to enable everyday pinch force measurement. The use of a smartphone eliminates the need for additional batteries and sensors, thereby reducing various costs associated with device creation. Moreover, with a focus on rehabilitating hand diseases and providing treatment for trauma, our goal is to create a readily available pinch force measurement device that can be used at home without the need for a medical professional. This device facilitates opportunities for pinch force measurement, contributing to hand health monitoring and rehabilitation. Studies in related research have focused on grip force measurement using flexible objects. There is a study that estimates grip force by analyzing the finger angles when holding a ball using a smartphone's depth camera. Additionally, there is another study using a ball with a built-in pressure sensor to estimate the grip force from the change in pressure when gripping the ball. However, challenges in these studies include limitations in the measurable range and issues such as the creation cost of balls with sensors. Furthermore, in research utilizing the magnetic sensors of smartphones or smartwatches, examples include magnetips and field sweep. Magnetips enables operations of smartwatches without touching the screen by attaching a magnet to the fingertip, and field sweep is a method to track the position of the smartphone by moving the smartphone over a board embedded with magnets. We propose a pinch force measurement using a built-in 3-axis geomagnetic sensor in a smartphone, along with a device embedded with magnets. By applying force to the device, as shown in the figure, the distance between the magnets and the smartphone changes, and the magnetic flux density changes. So this alteration is used to construct a pinch force estimation model. A 3-axis geomagnetic sensor is a sensor that acquires magnetic flux density in 3-axis, x, y, and z. A 3-axis geomagnetic sensor is used because there are directions that cannot be detected by a uniaxial or biaxial sensor. This is how it works. Users pinch the device between thumb and index finger and apply force. The upper and lower plate are connected by springs and pillars. The upper plate sinks when force is applied, and returns it to its original position when the fingers are released. We obtain the difference between the magnetic flux density at the start of the measurement and the maximum value during the measurement. The constructed device takes the forms in the figure. 2 aluminum plates are connected by 4 pillars and springs. Magnets are embedded in the upper aluminum plate, and applying pinch force causes the upper plate to move down via the spring mechanism, resulting in a change in distance from the smartphone. The The specification for the magnets, springs, and dimensions of the created device are as follows. Neodymium magnets with the strength of 240 militesla were utilized, and we use 4 springs with a maximum load of 43.25 Newton each, and the maximum load can be measured up to 173 Newton. Since 173 Newton is about 17 kilograms, and the average pinch strength of an adult is said to be around 8 kilograms, so we choose a spring that has enough durability to measure the pinch strength of an adult. The smartphone used in the measurement is Huawei P30 Lite. The smartphone's geomagnetic sensor is internally embedded in the upper left part of the smartphone, so to ensure optimal sensitivity of the sensor, the device is attached to the smartphone case, 5 mm from the top and 5 mm from the right edge, as shown in the figure. The device is mounted in a case so that the smartphone can be easily turned into a pinch force meter by attaching and detaching the case. In the measurement, a force gauge, as shown in the figure, was employed to apply forces ranging from 0 Newton to 200 Newton in increments of 5 Newton. The goal was to investigate the relationship between force and magnetic flux density, and to construct a model to estimate the pinch force from the magnetic flux density. For each measurement, the difference between the initial flux density at the start of each measurement and the maximum value observed during the measurement was calculated. The magnetic flux density was determined using the absolute values of the three axes x, y, and z. When expressing the result with a regression model, the graph appears as shown. The regression equation expressed as a function of force F and magnetic flux density N can be expressed as F equal minus 0.0003 times N squared plus 0.5091 times N plus 2.1704. This indicates there is a strong correlation between force and magnetic flux density. Since the geomagnetic sensor may be influenced by the surrounding magnetic field, similar experiments were conducted under two conditions: A, with the smartphone placed nearby the device, and B, with both the smartphone and the computer placed nearby the device. The devices were not moved during the measurement. The regression equation for these conditions are as follows. Constraints include the potential for errors due to geomagnetism. It is considered necessary to calibrate before measurement to eliminate this influence. Additionally, when using different magnets or springs, there is a need to reconstruct the regression model. And as future work, we plan to investigate compatibility with different smartphone models. Furthermore, to conduct user studies, we aim to improve usability, including device grip comfort, device weight, and device size. So this is all for my presentation. Thank you for your attention.